We all know that a program consists of code and data. When a program runs, code, data, and other components are stored in different memory regions which are logically divided. In this video, we will introduce the memory layout in C++ in detail. Alright, let's get started. During the execution of a C++ program, memory is divided into different regions to manage the lifecycle, scope, and access mode of data. From high to low addresses, the regions are stack, heap, global static storage area, constant area, and code area. Each memory region has different purposes and lifetimes. First, the stack area. This is a region that is automatically allocated and released by the compiler. Stack memory is managed by the system and includes function parameters, including the this pointer, return addresses, calling context, intermediate results from expression evaluations, temporary objects generated by the compiler, and so on. When a function begins execution, its required arguments and local variables are pushed onto the stack. After the function finishes execution, those previously pushed parameters and variables are popped off and released. Its operation is similar to the stack data structure. Stack memory allocation operations are built into the processor's instruction set, so the efficiency is high and allocation is fast. It only needs to move the stack pointer. The allocated memory blocks are contiguous, so space utilization is high. Each thread has its own stack, ensuring thread safety. The stack follows a last in, first out principle. Stack data is stored from high addresses to low addresses, so the most recently pushed data is at the bottom of the stack, while the earliest pushed data is at the top. When reading stack data, it is accessed from low addresses to high addresses. Second, the heap area generally stores dynamically allocated memory, such as memory allocated by malloc, calloc, or realloc. These spaces are usually managed and released by the programmer. If not freed, the OS may reclaim them when the program ends. However, if the program doesn't end, it can cause a memory leak. Therefore, dynamically allocated memory must be freed with free. Memory allocation in the heap is similar to a linked list. Typically, heap memory is allocated from low addresses to high addresses. That is, the memory addresses of newly allocated spaces are increasing. This is because the heap uses dynamic memory allocation, usually managed via linked lists or similar structures to track allocated and unallocated blocks. New allocations are added to the end of the list, so the addresses increase. When reading heap data, there's no fixed order from high to low addresses. Data in the heap can be accessed and modified via pointers as needed, not limited by the address growth direction. Global static storage area stores two parts of data, global variables and static variables. This space is managed by the system, allocated when the program starts and reclaimed when it ends. The data exists throughout the program's execution. It is further divided into two areas, the BSS segment and the data segment. The BSS segment stores uninitialized or zero initialized global and static variables, while the data segment stores explicitly initialized global and static variables. In C++, the compiler automatically initializes global and static variables. The constant area stores constants such as integer constants, character constants, floating point constants, and string constants. These cannot be changed during the program's execution. This space is managed by the system. Its lifetime is the same as the program's runtime. Const is a keyword in C++. A variable declared with const is treated as a constant and cannot be modified during program execution. Let's talk briefly about the difference between constants and variables. Constants cannot be changed during execution, while variables can. Once a variable is declared as const, it becomes immutable and is treated as a constant. The code area, as the name suggests, mainly stores the machine instructions of the program with compiled binary code. This region is typically read-only to prevent accidental modification of instructions. It is also shareable, so multiple instances of a running program can share the same code segment. This area is allocated by the OS when the program is loaded. In addition to dividing memory by functionality, we can also classify it by usage state. When a program is loaded into memory, it has two attributes, statically allocated memory and dynamically allocated memory. Statically allocated memory refers to memory determined during compilation and linking. Dynamically allocated memory is assigned and reclaimed during program loading and execution. Their differences mainly lie in two aspects. Time. Static allocation happens at compile link time. Dynamic allocation occurs during program loading and execution. Space. The heap is always dynamically allocated. There is no static heap. The stack supports both static and dynamic allocation. Static stack allocation is done by the compiler, for example, for local variables. Dynamic allocation on the stack is done using functions like malloc. However, dynamic allocation on the stack differs from that in the heap. It is handled by the compiler and doesn't require manual implementation. Dynamic memory allocation refers to the method of allocating and reclaiming memory dynamically during program execution. Unlike static methods like arrays, which require a predefined size, dynamic memory allocation is handled by the system as needed, and the allocated size matches the program's request. If we relate this to the 5 main memory regions, Statically allocated memory includes the global static storage area, data segment and BSS segment, constant storage area, and code area. Dynamically allocated memory includes the heap or free store. When dynamically allocating memory, we commonly use new or malloc to request memory and delete or free to release it. As you've likely noticed, new pairs with delete and malloc pairs with free. So, what are the differences between these two pairs of functions? First, malloc and free are functions, while new and delete are operators. Second, memory allocated by malloc is not initialized, whereas memory allocated by new can be initialized, though built-in types with new are not automatically initialized. Third, when using malloc, you must manually calculate the number of bytes to allocate. With new, you just specify the type. Also, malloc returns a void, which needs a typecast, but new doesn't because it includes the type. On allocation failure, malloc returns a null pointer, while new throws an exception. For user-defined types, new and delete call the constructor and destructor, while malloc and free do not. In a computer system, data storage and retrieval are typically done in bytes. For a single byte of data, whether in the heap, stack, or other memory regions, storage and retrieval are from low bits to high bits. In C++, data types also follow this principle. For example, integral data types like int and long usually occupy multiple bytes, and each byte is stored from the least significant byte to the most significant byte in order. When we read an integer variable, the computer starts from the least significant byte and reads each byte in sequence, then combines them into a complete value. This is known as little endian byte order, which is the standard on most processor architectures. Note that some hardware platforms or compilers may use big endian byte order, where data is stored from the most significant byte to the least. But big endian systems are relatively rare, and little endian is the common standard in C++. In general, in most systems using C++, data is stored and read from low addresses to high addresses, which aligns with little endian order. That's all for this episode. If you want to see more videos like this, please like and subscribe. If you have other topics you're interested in, feel free to leave a comment below. Thank you all.